our, let's see, it should be on our, there will be a button on our main page on where the YouTube channel is. I will put that YouTube channel in the announcement. Oh, it's in the announcements already. In the announcements, you'll find the link to the YouTube site for the lectures for nanocomposites. And so if you wanted to go review something or look at something I said or giggle about me saying something wrong, go ahead and review that if you want. But that'll be there. I'm going to include a button eventually on the home page that'll take you directly to that. But this will also be posted on there so that we can, you know, anybody who misses class can catch up and see what we're working on. So that being said, does anybody have any questions about Polymer so far? Okay, let me go ahead and let's see, I minimized something somewhere. There it is. All right, let's build that back. All right, so I have that now. Okay, so what I'm going to do is I'm going to go ahead and share my screen. Let me plug my computer in. It's not going to share that way. And my AirPlay. Let's Okay, so here's where we were yesterday. We had talked about how these crystals will grow from our polymer. And in this case here, we're looking at them growing in a radial fashion. And so what's really happening is in each of these, you're starting to see that lamellar formation where you have the polymers are folding over and lining up on each other and growing out axially. And then when there's defects where they split into two crystals, they continue to grow out axially, and then they can split and they'll go out. And so that's why it looks like they're going out in a radial or in forming a circular pattern as they come out like that, because they're forming those lamella that then split and then continue to grow and split and continue to grow. So what does that really look like? If we take a look at this model here, based on the paper we saw that experiment done, we'll see that there's going to be some little defect where they start to grow, okay? And then as they start folding over on themselves, right here, they're going to grow out in this direction here. So this is growing in the radial direction. But every once in a while, there'll be a defect where another one will split off. And so we'll have another one growing in this area, and another one growing in this area, and then another will split off, and then it'll grow into the other area here. So you'll see how that even if we start with a single lamellar structure growing from the center defect, it'll continue to grow out in that, and then the defects are going to create that wedge-like structure that creates the spherulite as a whole. Okay, so do you see how those individual, when they, you know, reach their max that they can order, they'll split out and form additional crystallites in there. And again, all that space in between, in the case of this here, we're gonna, where's my pictures? Oh, they're there. There they are. There, okay, blue. All this space in between right here, that's non-crystalline. So that's the free volume area. All of the space in the other section is the, where is it going? Not that. All the stuff here is crystalline. All the stuff in the middle in between is non-crystalline. So that's why we really never have a fully crystalline polymer when they grow this way. I bet it's only about 60 or 75% crystalline because we have that free volume in between those spherulites. All right, questions on polymer crystallization and or spherulites? Okay, so let's think about this. Do spherulites help or hurt us when we try to put a nanomaterial in? Depends on the nanomaterial. Sometimes it helps us, sometimes it hurts us. Sometimes the nanomaterial helps form the crystals. Sometimes the nanomaterial hurts forming the crystals. So we're going to see both cases where we have increased crystallinity because of a nanomaterial or decreased crystallinity because of a nanomaterial. So we have to keep into account, you know, number one, what's the polymer's natural propensity? Does it want to crystallize? Does it not want to crystallize? And then adding the material, is that going to help it or hurt it? And then we also have to think about processing. Remember, processing enhances or decreases crystallinity. If we slow it down fast, it decreases crystallinity. If we draw it out or slow it down slow, it increases crystallinity. So processing, material, and additive are all going to change the crystallinity of our polymer system. So we have to pay attention to each of those aspects. All right. So the last thing I want to talk about in polymer chemistry is when we have block copolymers. This was really big back in the 90s when I was in grad school. And so what we saw is that block copolymers have different morphologies based on the segregation of the different blocks of the polymer. So let's say you have a big long block of one thing and it tries to exclude the shorter block of another thing. You're going to have a different morphology than if you have two blocks that are exactly the same length and still try to exclude each other. Let's say one was going to be, more hydrophobic and one's less hydrophobic. They're going to try to be in their own regimes. And so we see different morphologies in the polymer, bulk polymer, than we would see in the non-block system. So the way we look at this is we have different formations form based on the different volume fractions of the different types of blocks. So again, a hydrophobic block or a hydrophilic block or a polar block or a non-polar block, etc. You would have these different things. And so if you start out with this segment here is going to be maybe 10% of the total length of the other block, we're going to see it segregated into small individual dots that are separated from each other, okay? Because there's not enough polymer, only 90% of it is the one block, only 10% of it is the other block. Let's say we increase that concentration to maybe closer to 2080. What we'll see is a different structure because we'll have more of the volume fraction is that smaller block. And because there's more of that fraction of the smaller block, it can start to form the spheres, but then can grow out into these long columnar structures or cylindrical structures. And notice that we still have the bulk of the material here is that other block. The 80% is still that other block. Only 20% is the small block that is being excluded from the free volume of the main block. Now, once you get closer to 50-50, that's when you start to get a block copolymer laminar structure or lamellar structure. Now, in this case here, what we're seeing is actually one block is excluding the other block, and then we're seeing that the other two ends are growing into its own lamellar structure. Then those two ends are growing into a separate. So if you can imagine, we have two ends, one's going to be hydrophobic, one's going to be hydrophilic. Then we're going to have inside that joint here is where we're going to see the two different segments. That's where the one of the centers of the polymer is going to be, where one branch is going to be hydrophilic and one branch is hydrophobic. And then that's where we're going to see those lamellar structures. Okay. And so again, all of these images are seen under cross-polarized light, where we're seeing just a little bit of rotation so that we can see that morphology. Now, if we go from that 80-20, like here, to a 20-80, we see an inversion of the two phases. Obviously, the 80% version has a greater volume fraction of there, and therefore it is the main bulk. It is the continuous phase there, and the smaller fraction becomes the discontinuous phase, in this case, columns. And if we go even smaller, we're going to get to those isolated spheres of that lower volume component. All right, questions about morphology of block copolymers? Okay, so the size and form of these, it depends on how we age. Typically, these are done where we do a slow cool and or an annealing process to get these larger regions to form. But even on a microscopic level or a nanoscopic level, these regions form even when they're slowly cooled down. It's only when they're very large do we see them with the cross-polarized light. All right, and so another form of another problem of crystallinity in polymers are what we call liquid crystallinity. Now, in liquid crystallinity, you expect a pure liquid that doesn't have liquid crystals to be kind of all disordered and all going in all different places, sliding past each other. That's what a liquid is, right? It has enough energy that it'll slide past each other without much force, okay? So most of the time there's no order in this, and you can tell this by taking cross polarizers and looking through your solution and seeing that there's nothing that is going to rotate light. However, crystalline solids tend to have some type of order, and therefore they're going to have different refractive indices as you go in and out of crystals. Therefore, you should be able to see them through these cross polarizers. You should see differences in that refractive index. Now, liquid crystallines are liquids that can arrange in order. Sometimes they arrange with shear, sometimes they arrange without shear. So there's different ways to do it, but a lot of times it can be, for example, LEDs, liquid crystalline displays, they actually align them by doing a wiping process, which gives a weird alignment on the surface of the polymer, and then the liquid crystals line up with that. And then you can rotate them using an electric field. Okay. So in the liquid crystals, there's some form of crystallinity, even in the liquid state. Even if they're flowing past each other, there's still some crystalline regimes. And so we call those liquid crystals. Now, it's not a fourth state of matter. Technically, the fourth state of matter is plasmas, but it does have some attributes of liquids, but some attributes of solids. So it's kind of an ordered liquid, if anything. So the ordered regions tend to be called mesophases, such that they are the ones where we see the stacked ordered system. And they're not exactly liquid because they're kind of held in with a pseudo intermolecular strength that kind of holds them into a position. Now, if that goes from the liquid phase and goes a little more rigid, then we call those things that order in that area, we call them mesogens, which means they're like the big flat things that'll order together. So if you have them shearing across each other in a solution, the mesophase is created by those flat rigid groups called mesogens. Now, these can be on the sides of the polymer chain, sticking out the sides like in polystyrene, but imagine a very long, rigid, flat molecule hanging off there, or they can be along the main chain. And so when they're on the sides of them, they're going to make slightly different mesophases than if they're on the main chain. And you can actually see everything from discs to spiral discs to all sorts of longer straight crystals on these things, depending on how those mesophases order in the solution and or melt. Okay. In fact, I did a project where I took a liquid crystalline polymer and I was trying to incorporate nanomaterials into it, but we had to actually modify the nanomaterial to have a liquid crystalline phase as well. And I'll tell you about that later. Okay. So one of the weird things about liquid crystals is that they can change their morphology either by a magnetic field, an external electric field, or even shear. Okay, so shear can actually change the order of these things. So if you can imagine shearing them and you can change color. They may also be thermochromic, meaning that when they reach a certain temperature, they switch from one mesophase to a different mesophase. And those different mesophases might have different colors or different transmission of light through them or reflectivity of light. So we'll see that they will change. And so an example of that would be a color changing thermometer that you put on. But almost all see some kind of high optical rotation. That's why viewing them in cross-polarized lights is most common. In fact, most LCD screens have a polarizer on that screen so that you can actually see the motion. You pull that polarizer off, you will not see that at all. It'll just look like white light. Okay, so that polarization, that need for a polarizing film to see them is very important. And then, so when they are liquids, they tend to be opaque. And when they're disordered, they tend to be transparent. When they're crystalline and ordered, they tend to be opaque. You can actually have those switchable windows for your bathroom that'll go from transparent to cloudy white And in the transparent state, they are non-crystalline, they're not ordered, they're disordered to allow the transmission of light. And in the crystalline state, when they apply electric field, they now have order in between the two electric fields, and therefore they create the crystalline, and then they diffract light, and it becomes opaque. All right, questions on liquid crystals? All right, so there's a couple different kinds. There's one that changes with the solvent. And so if you have them in solvent at different concentrations or different shear, you can see them happening in that solvent. And those are called lyotropic, meaning that it's within a solvent and they're different forms. Then there's a type called thermotropic, which means you do not have to have solvent. They'll naturally form these in the melt or in the, with flow in melt, but there's no solvent required. But they can make different types of phases. The phases include pneumatic phase, which is kind of all aligned, a smectic phase, which actually has layering in it, must have layering in it, and cholesteric is more of a larger group of materials. Okay, and it's akin to the cholesterol we have in our bloodstream. Okay, when we actually study any type of liquid crystalline polymer with a nanomaterial in it, we're going to describe whether it's a pneumatic, a smectic, or cholesterolic phase, and whether it happens in a solution or in melt. All right, any questions? Okay. So the net takeaway is polymers that we're going to be using typically have an organic component. We're going to be looking at a lot of different polymers. Most of them will be commercial polymers. There's a lot of engineering work done on loading of commercial polymers with nanomaterials to change their properties. Now, the polymers themselves have melt, have flow, have solubility, and that's all based on the type of functional groups they have and the type of intramolecular reactions they have. Those same intramolecular reactions between polymer chains are going to dominate whether or not the nanomaterial is incorporated well or not. So those intramolecular forces between polymers are as important as the intermolecular forces that we'll see between polymer and nanomaterial. So those are things that we're going to see again and again and again. So just make sure you have those kind of concepts at least very familiar in your head. All right. Okay, so now we're going to switch over to nanomaterials. So now that we have the polymers, we're going to put the nanomaterials in. Let's go ahead and switch over to nanomaterials. Okay, so nanomaterials and how to define them, or where to define them, depending on how you're going to look at this. So basically, in the book, as we're actually kind of starting with the first 2 chapters in the book here, nanotechnology technically is any technology operating on the nanoscale. Now, nanoscale is defined as between 1 and 100 nanometers. That means most individual atoms are below nanoscale. They are less than 1 nanometer long, okay? So we're not talking about atomistic. We're talking about clusters of atoms, okay? And up to 100 nanometers. Once it becomes above 100 nanometers, we're looking at a micro scale, not a nanoscale. And so we have that narrowly defined region of those 3 orders of magnitude from 1 to 100 nanometers. So that means that anything we incorporate a feature that's small in can be considered nanotechnology, whether it is naturally occurring or formed that way, or like we're going to be doing is intentionally incorporating a nanomaterial to change its functionality. Okay, so when we're talking about nanotechnology, we want to look at it as you are only going to add it to create some significant difference in the chemical, the physical, the biological, the processing, the phenomenon, or there's no reason to incorporate your nanomaterial. Okay, nanomaterials are not cheap. You always do it to improve or decrease a certain property in the system. And so what we're going to see is most of what we're going to do is we're going to enhance a property by adding a nanomaterial, and sometimes we can decrease a property by adding a nanomaterial. Okay. All right. So when we talk about nanomaterials, that means we have to have at least one dimension in the nanoscale. So if you think about it, So if you have something like a single atom, that is not in the nanoscale, but a cluster of atoms would be in the nanoscale. And it would have a 3 dimensions, it's nanoscale in 3 dimensions. So we have to think about how many dimensions the material we have is on the nanoscale, because our materials in that nanoscale have very different reactivity, very different properties than on the macroscopic scale. They have a very high surface area, and that means they're fairly reactive. The reactivity can change. Imagine a nanoscale catalyst versus a microscale catalyst. Many, many more reactive groups, therefore more reactive. It actually changes the melting point. Melting point is usually considered a colligative property. It does not change with sample size. That is true until you get below the microscale. In the nanoscale, you change the melting point. Typically, the melting point goes down because the higher surface energy. It would like to reorder to become that more bulk-like material. Its interaction with light. Once you go below 1/10 of a wavelength of light, you stop interacting with the wavelength of light, and therefore you can stop seeing certain colors of light with certain sizes of particles. And I'm going to demonstrate that on a couple slides. So that means we want to look at things on the nanoscale because we can see things that are very tiny. We can avoid light, or we can interact with light in a certain wavelength. We can change morphology because it can pull polymer chains together or push them apart. We can look at an interfacial phenomenon, have it come to a surface and be a barrier or be easier to rub against or have more tribological effects, or even quantum effects where it's not interacting with this wavelength of light, but when we create a phonon inside the material, it actually will emit light. And so I have a couple projects on surface enhanced Raman spectroscopy that use that concept of exciting and having it emit light from those nanoparticles. Okay, so to kind of get things on scale of what that order of magnitude is if we think of a single carbon nanotube, okay, it is 100,000 times smaller than a human hair, okay? So if that is true, then our human hair is actually 100,000 smaller than a house. Okay, so if we're thinking about that, so compare your house to your a string of hair, and now think how much smaller it has to be a single-walled carbon nanotube that's only 1 nanometer wide. Okay, so the scale that we're talking about is really, really small. And think about your hair is going to be in the micro scale, where this is going to be in the nanoscale. If we look at that more on a particle size, when we look at more 3 dimensions, a nanoparticle of a collection of approximately 1,000 atoms, gold atoms, would be about 4 nanometers across. That is 1 million times smaller than an ant, which is 1 million times smaller than Indianapolis Motor Speedway in Indianapolis, Indiana. So, or some of you may know it as the Brickyard. So the idea here is that not only is it so small, it changes its reactivity, it's so small, we have to change our way of analyzing these materials to see exactly how they're influencing that our properties. All right, questions on just the scale of things. Okay, I used to have this wonderful thing online but they took it offline, but it was really, really cool. What it did was it started with the universe as a whole and kept going down and down and down and down and got to, solar systems and planets and atoms and then subatomic particles and everything like that. And it was this order of scale of sizes all went from femtometers, which is below nanometers. It's 10 to the minus 12, I think. And all the way up to nanometers, which is, the highest level of things we can see on the SI scale. So I think it's ADA, NADA, something like that. Yeah. Anyway, so it was really cool. It showed you going all the way through the nanoscale, even subatomic, etc. All right. So if we're looking at nanoscience, we want to look at things at least one dimension less than 100 nanometers. Sorry, there's a mistypo. There's a typo here. 100 nanometers. Okay. And then we have to actually use different methodologies to figure out why it's changing the characteristics. Again, the bulk properties that we see in large scale materials don't always react the exact same way. Now, the fact that we have a different physical or chemical interaction with this on a molecular scale tells us we actually might have a different process or a different bulk property on the bulk scale, on the macroscopic scale. So those individual chemical interactions are going to be the influence on our macroscopic properties. And that's what we're going to see in most of these systems. Okay. Ooh, okay. So if we think about how we're going to deal with these things, an actual individual polymer all by itself, kind of rotating around in solution, might be approximately take up a volume with a diameter of approximately 40 nanometers. Okay, so those are individual polymer chains that are maybe, you know, a couple 100,000 molecular weight, are very small. Well, quantum dots, for example, those that interact with light in a very specific way, are much, much smaller. They're only about 7 nanometers. Okay, now some of the other things we can see that have very long rods of metals like gold rods that interact with light to give us different colors are actually higher. They're 30 nanometers long, but they're only 3 nanometers in diameter. So that aspect ratio gives us two effects. One, a 3 nanometer effect, but then they also give us a 30 nanometer effect. So aspect ratio is going to have an effect on our materials as well. And then, of course, they're comparing it to the size of viruses, bacteria, and blood cells. So, but we're talking, you know, imagine that a polymer, an individual polymer at 40 nanometers can interact with materials that are 1, 5, 10, 100 nanometers large or small. Okay, so let's start talking about the number of atoms necessary to make that. I said that atoms themselves are too small. They're less than 1 nanometer. We have to have clusters of atoms to get us into the nanoscale. So an individual gold atom right here would be below 1 nanometer in diameter. You know, it's like 2.5 angstroms, okay, which is 0.25 nanometers. So we can't have individual atoms in the nanoscale. We must have clusters. And then when we get to clusters, we can start with small number of clusters. And like one of the smallest ones that I remember is close to about 80 atoms, like 80 silicon atoms in a nano silicon material. And that was right around 1 nanometer. And then as you got up to higher and higher numbers, in at least the gold here, you have to have over almost 3,000 atoms to get a 4 nanometer sphere. And then you almost need 10,000 to get a 6 nanometer sphere. And you need over 50,000 to get a 10 nanometer sphere. And if you think about that, it's because it's growing in a radial sense. It's growing in all 3 axes all at the same time. And therefore, the number of atoms requires to fill that volume. So it's going to be 3 pi r squared 4/3 or whatever. So you're filling it up in a volumetric sense. So that's why it's taking so many more atoms just to gain that little bit of diameter change in our spherical nature. All right, questions on that? Okay. So size, I said, you know, there's different ways they're going to interact. They have higher surface energies, which is going to change their melting point. But there's also different interactions with light. One of the best representation of that is actually these gold nanoparticles. So when they started doing gold nanoparticles, one lab would report one color and one lab would report another color, and they'd say, oh, so they finally got to analyze this using dynamic light scattering and tunneling electron microscopy that would say, okay, the different colors actually are different size gold spheres. And it's because they're reacting with different they can only interact with different kinds of light. For example, the smaller the one has to be only interacting with the blue light, meaning the red light comes through, and we see that red color. As they get bigger, it starts interacting with the longer wave red light, and it starts to turn blue. So we start to see this color change based on the wavelength of light it can interact with. Okay, here's a question. When was the first nanocomposite ever made?
I think it was like 89.
Older than that.
Oh,
Nanocomposite, first nanocomposite ever made. It's earlier than 89. It was around 1500, okay? They didn't know they were making nanomaterial, but they were. When the artisans who were creating glass for stained glass, they worked for all these different ways of creating all these different colors, and they got blues and they got oranges and everything like that. But red, bright red, they did with taking gold and urine and adding it to the glass system, and they accidentally created gold nanoparticles. They didn't know it at the time, but it was the only place that you could get this bright red. And subsequently, back in the 80s and 90s, they went back and reanalyzed these gold these gold glasses that were done back in the 15 and 1600s, and found out they had gold nanoparticles in it. In fact, they were 2 to 5 nanometer gold particles, depending on which place that were made it. And so that's how old nanotechnology has been used, whether we knew it or not. But taking from those people who just figured it out by accident, we've been able to add on knowledge, add on knowledge, and add on knowledge. And when I studied this back in the 1990s, it's actually come a long way since then even. We've got a lot more precise in how we can order these and how we can incorporate them. But anyway, any questions on gold nanoparticles? Or yes?
Can you please tell me why they have to exist in cluster form?
Okay, so in an individual gold atom would be less than 1 nanometer, right? So if you have to have more than one, they're going to cluster together, and a metal bond, they like to share electrons, so they're going to cluster together. Most of the time, they're going to cluster together in a crystalline form. Okay, so that's why they form clusters. Okay, an individual atom is too small. You have to have clusters to make it large enough to be that. Now, why are the surface of these clusters more reactive than bulk gold? Okay, if we think about bulk gold, we have millions of atoms across this surface and a little bit of oxides there. And in the bulk, if you look at any one gold atom, it sees the 8 atoms around it, and then the atoms around that, and the atoms around that. Okay, so there's only 0.1% of those gold atoms that don't see all of its other neighbors. Okay, now let's look at a small particle right here. Okay, about, in this example here, 10 to 15% of those atoms in that cluster don't see all of the 6 or 8 atoms that it should see in its bulk form. So that means all of the ones on the surface and all the ones near the surface have vacant valencies where they could put other atoms. So that means that's a higher energy state than if it was buried down in the middle of a piece of bulk gold. It's going to have all of its neighbors satisfied. When we have a cluster like this, every atom on the surface is lacking 2, 3, or 4 atoms. And that gives it an intense surface energy. That intense surface energy lowers the melting point, increases its interaction with polymers and polar groups, and increases its propensity to glob together to form larger clusters. Okay, does that kind of answer the question about?
So, yeah, so they only exist in the crystalline form, or they can be amorphous form as well?
They can be amorphous as well. It depends on how you grow them. For example, you can create perfect nanosilicon crystals, silicon, elemental silicon, and they will be perfect if you grow them one way. If you do them another way, they are perfectly amorphous. Okay, so I've published in both amorphous and non-amorphous crystal, and it's all about kind of rate and process. In making amorphous clusters, we actually made them in a process that only took 10 minutes. The crystalline ones took a little bit longer and higher temperature. Okay, so it can be either one. Most of the time though, if it's an oxide or a metal particle, it's going to have some crystallinity. You have to try really hard to make it amorphous, but they will note that. Okay, all right. So now that we're talking about these clusters and how we can see cluster size changes its interaction. And in this color example, it's just changing the interaction with light. But you will see that same change in interaction with your polar groups on your polymer, pi stacking on your polymer, hydrogen bonding on your polymer. All these different things will also interact in a very different way than in the bulk. So when we talk about polymer nanocomposites, we're typically talking about improving one or more properties at a time, but there are some disadvantages. So we can improve the mechanical properties of something. We can make it tougher, making resistant to impact. We can make it stiffer, resistant to flex. We can make it higher tensile strength, resistance to pulling, right? All of those usually have some kind of mechanical, it's some kind of greater interaction with the filler, and the filler has a higher tensile strength or stiffness or toughness than the polymer itself. So we're adding the nanomaterial property to the polymer property. The other thing we can do is gas barrier. So when we permeate gas through a polymer, first thing you do is absorb the gas to the surface, then that dissolves into your polymer and then permeates by diffusion and then gets to the surface of the polymer and degasses on the other side. Okay, so what if you had a nanomaterial that was like little plates of glass in there, and then so your gas would have to go onto the surface, dissolve into the surface, diffuse, hits the little thing of glass, has to go all the way around that piece of glass, diffuse down and go all the way around another one and keep doing that. In that case, our nanomaterial is acting as a barrier to gas, and therefore it increases that gas impermeation property. Then there's also, we can do flame retardancy. Okay, one of the classic ways to do a synergetic flame retardancy of an additive is to have a smectic type clay, and we're going to talk about that. That's a clay with a bunch of layers with something in between. And by having things like water in between, as your thing burns, the water in between the little plates expands and goes puff, and that releases water vapor and that quenches flame. And so we can actually have flame resistance just by having this additive be in our system. Then we can also do dimensional stability. Dimensional stability, what does that mean? That means it doesn't expand or contract with temperature or deformation. So if we had a polymer that's normally a little bit squishy and would expand and contract, give us more free volume or less free volume during our heating and cooling stage, but let's instead throw a bunch of little sticks in it, like a whole bunch of randomly designed crystals in there. Now it would have to slip past these crystals to expand and contract. So you can actually minimize the amount of shrinkage and expansion during our processing, and it can also keep things from creep. So instead of having it slowly squish down over time, those internal nanostructures will keep it from doing that. So thermal expansion, it's the opposite of that, where it's keeping it from expanding by going past those little crystals. We can also increase thermal conductivity or electrical conductivity, or both, one or the other or both, by choosing your nanomaterial. Thermal conductivity, a great way to do that is to put something that's highly thermally conductive. So copper powder or graphite powder or graphene, all of those are very thermally conductive. But They are also electrically conductive. What if you want thermal but not electrically conductive? Then you have to go to things like nanodiamond, hexagonal boron nitride. These are things that conduct heat, but do not conduct electricity. So you can choose thermal property, electric property, or both based on that system. Okay. Then we can also improve the properties of ablation. Ablation is all about wear along a surface. So what if you had a polymer or maybe a polymer composite with carbon, and you're putting something across it? It's very abrasive. Like imagine the nozzle of a sandblaster, right? You could add additives in a small amount to your polymer matrix that would resist that ablation. Things that resist ablation are things like zinc oxide or what's the other one? Zirconium oxide are very resistant to abrasion, but they're expensive. What if you just incorporated a small amount into your matrix such that it would resist ablation, and therefore you can have a little bit in there and still have your ablation resistance? Chemical resistance, just the process of having some nanoparticle that is adhered to it, or it has a strong molecular interaction between the nanomaterial and the polymer, makes it very resistant to being dissolved. If it's resistant to being dissolved, it's less resistant to chemicals. Okay. Reinforcement usually means some kind of mechanical reinforcement, and you can do that in 1, 2, or 3 dimensions. And then you can actually do multiple properties. You can do it thermally conductive plus thermally expansive. So you can have something that self-limits its electrical conductivity by expanding and contracting. So there's multiple ways to do that. Unfortunately, some of the things that we add to them have disadvantage. For example, viscosity increases. Okay, so imagine you have a polymer that will melt. By adding a bunch of things that are restricting the polymer chains flowing past each other, you're going to change the viscosity. You're going to increase the viscosity, making it more difficult to process. Then we also have the idea that to get the best property possible, let's say you want to do electrical conductivity, you need to have a whole bunch of these different little plates all separated out at least about, the electrons can jump about 20 angstroms. So you want them easily separated as much as you can. Sometimes it's very hard to disperse that because of the interaction between the nanomaterial and the polymer, or the nanomaterial and itself. If it has a stronger interaction with itself, it'll be difficult to disperse. If it has a better interaction with the polymer than itself, it'll be easier to disperse. Optical issues, again, trying to get things dispersed correctly or having small crystalline segments will give us optical issues. If you're doing it in solution, big problem is sedimentation. Having your larger particles or your non-dispersed particles separate out. And then you have problem where if you're using carbon nanomaterials, you tend to basically, you can choose any color you want as long as it's black. The old Henry Ford thing, where it's, if you're going to use carbon to increase your conductivity and or thermal conductivity, it's always going to be black. All your tires are black because of carbon. Okay. Questions on different characteristics and properties. Okay, so when we want to improve a property, we have to choose our nanomaterial correctly. And when we want to minimize our disadvantage, we have to choose our aspect ratio carefully as well. So what do I mean by that? Well, turns out nanomaterials only have to be nano in 1 or more dimensions. Okay, so let's think about that. If we have something that, let's say, looks like a piece of paper, okay, and it's more than a micron on this side, more than a micron on this side, but the thickness of it is effectively in the nano regime, we have what we call a one-dimensional nanomaterial. Okay, only that one dimension is a nanomaterial. And we can think of this as things like Montmorillonite clays, and I'll talk about clays in a minute, graphene sheets, or double layer hydroxides, which are typically synthetic metal hydroxides. Okay, so that means only one of those. They tend to be very large plates with only the thickness is in our nanoscale. Okay, now the second way we think of it is when I looked at those concept over here of the nano rods, where we had the diameter was in the nanoscale and the length was greater than nanoscale. But if the X and Y are in the nanoscale, i.e. the diameter of the thing, the length of the rod can be anything in the nano or outside that nano regime. Now, when we talk about fibers, we're typically talking about things where the aspect ratio is very high, such that the length is outside of the nanometer range, greater than 100 nanometers, but both the X and Y axis of the diameter are within that nanometer range. And when we think about that as carbon nanofibers and carbon nanotubes, and they're different, I'll show you what the difference is. And then we have natural clays that actually do this as well. Plus we have synthetic nickel or metal nanostrands that can be used. Okay, then the last thing we want to look at is a three-dimensional scale. In the three-dimensional scale, that means that you have X, Y, and Z are all within that nanometer scale. So these tend to be particles, and they have less impact on the solution or the melt viscosity than the plates or the fibers. So we can actually go to a particle to minimize our viscosity issues, where our fiber or platelets might have those issues. So choosing our number of dimensions and using our type of material is important. Now, the other thing about choosing our material is what property do we want to enhance? Do we want to enhance only mechanical properties? Do we want to enhance only electrical properties? Do we want to enhance only thermal properties? We have to pay attention to which of those we can, because carbon nanofibers, yes, they will enhance our mechanical properties. They will give us higher tensile strength, but they're also going to make things more conductive, okay? More thermally conductive and more electrically conductive. So how do we do that? Well, we choose a fiber that is not electrically conductive, okay? So again, it's choosing our material and then choosing something, the polymer that it's compatible in. All right, questions on different types of nanomaterials? I'm going to go through each of these individually, by the way. Okay, so this is another way of looking at it. In our one-dimensional, think of plates or sheets or things like that, where they can be slipped apart. So if you can imagine mica or something where the planes will slip across, molybdenum sulfide, you can slip those planes apart. And in the thickness of the layer they have, it is in the nanoscale, but the plates themselves are outside of the nanoscale. Okay, so then when we talk about two dimensions, we're talking about large aspect ratio fibers. Okay, so the X and Y of the diameter are in the nanoscale, but the Z axis is out of the nanoscale. If the Z axis in the nanoscale, it turns into a particle because it's closer to the three-dimensional. All three dimensions, X, Y, and Z, are in the nanoscale. Therefore, it falls under particle. So you can have a very short fiber that still falls under particle, but if it's a very long fiber, it falls under two-dimensional fiber or filament. All right, questions on that? Okay, so before I go any further, I have to kind of talk about some of the one-dimensional aspects here, and then I'm going to break and talk about clays in particular, because they are a naturally occurring material that tend to be a little bit cheaper and they're used extensively. So we got to talk about those as a separate class. So the first thing we want to talk about on our nanoscale dimensions or our lamellar nanostructures is Montmorillonite or bentonite. And it's a naturally occurring clay. And what we have is aluminosilicate layers that have water and or counter ions in between the layers. So the individual layer between the different aluminosilicates are in the nanoscale. However, they can form large crystalline plates, and these large crystalline plates stack on top of each other. And by including water or large ions or something in between the plates, you can get these plates to come apart, and that's called exfoliation. Okay, so when we look at that, we want to see something where we can get a solvent or an ion in between these plates. And if we do that, we can spread those plates apart. And if we spread them apart far enough, we can get a polymer in between them. And once we get a polymer between them, they're dispersed into our polymer system. So that's one thing we'll talk about. Then the other thing we have is things like graphene. Okay, graphene platelets are only 1 carbon thick, so technically they're a little under nanomaterial, but they have a large structure in the X and Y, in the Y and Z planes. So we consider them, and they actually do very well at dispersing into certain polymers through their pi stacking interaction. And let's see, then the last thing I want to talk about is metal hydroxides. And metal hydroxides are similar in structure to Montmorillonite, which is a naturally occurring aluminosilicate. However, they tend to be synthetically made and use other metals like nickel, iron, magnesium, bidentate or tridentate ions that are mixed. And the feature that these hydroxides have is you have hydroxides on both of the top and bottom surface of the main plates that you'll see. And I'll talk about those also separately. So the last thing, okay. So let me talk about Montmorillonite first. Montmorillonite is what we call a very soft phyllosilicate, meaning it's an aluminosilicate, but it has layer-like structure. So it's soft because you have one plate laying across the other plate. The only thing holding those plates together is maybe an ion or two and maybe a little water. So what happens is they can slip across each other. And because they can slip across each other, the macroscopic strength of these is very, very small. And so they can be processed by pushing water in between the plates and getting to an exfoliant. This whole class of compounds known that can be exfoliated in water tend to be called clays. Okay. Now, this particular kind of clay is what we call a Spectite group. A Spectite group means that you have a total layer of tetrahedral, octahedral, tetrahedral. So you're looking at aluminum, silicon, aluminum, all in one layer. And then there's hydroxides on either surface. And then there's usually a little bit of water and a counter ion, something here, depending on where it was made, when it was made, at the bottom of which open, you're going to have sodium ions, potassium ions, magnesium ions, etc. Sometimes you can have even iron ions, and these clays will actually be a little bit red. Okay, so we have our aluminum here in the middle, right here, our silicons on the outside. Actually, let me change colors for the silicon on the outside here. And then all the empty valences are held by oxygen. Okay, and then hydrogen wherever the oxygen are. So this bilayer of silicon, aluminum, silicon, it makes up the entire long structure, but that is the nanoscale portion of it is the silicon, aluminum, silicon case. So this is one type of clay. Let me tell you a couple things about other types of clay. So the Spectite group actually has about 20 different things in it, different kinds of ways to stack aluminum and or silicon together, because those are very common in their crust. Okay, and so it's always that 2-to-1 structure of silicon, aluminum, silicon. Okay, now in case of other things, we can actually have a different ratio that doesn't necessarily have a 2-to-1, 2-to-1. It'll have a 1-to-1. And in the 1-to-1 things, we call those kaolin clays. The most common of those is canalite or halloysite. Halloysite turns out to be a single layer of this aluminum silicon that wraps around itself to create needle-like structures. So if we look at Montmorillonite, Montmorillonite has the possibility of being expanded by pushing more and more water through it. And so if we look at this picture here, we can actually see the beginning of a flat piece of Montmorillonite actually starting to exfoliate, starting to have solvent, or yeah, it's solvent in this case, but we can do it with polymers too. Spread those individual layers apart. And once those individual layers get spread apart and have polymer between them, we now have our true nanocomposite. Okay, so in the case of our halloysite, we have 2 dimensions that are on their nanoscale. So these are these long fibrous needles, but we have the X and Y of that diameter that falls under that 2-dimensional scale. And these create long, stiff needles. And that makes them actually easier to disperse in water than the smectites because there's less surface area in between each of the individual fibers. And halloysite can be dispersed in water very readily compared to hours or days for the counts of Montmorillonite. Okay, then there's a less known type, which we call the illites, which are like the Montmorillonites here, but the ions in between them are so tightly bound, they don't swell with water. So they might have a little bit of water in there, but they're going to have a different ion in between, and therefore they don't swell with water. However, they do sometimes swell with heat. So if you think of it more like a mica that you heat up and it pops up. Okay. So the next, it's not commonly used as a nanocomposite, but it is in the process, is what we call a chlorite group. Those tend to grow more like those crystals that grew in polymers that grew into the spherulite type formations. It's similar to the oxide, but instead of being an oxide or hydroxide, it actually has a chloride or other halogens in there. So there's metal halogens that are mixed stacked, and they give us this polymer structure. So basically, that's a 1 or 2D structure. They can be lamellar or columnar, but those are not typically used, but they are a class of clay. And then the last type we're going to use is also a 2-to-1, like the Montmorillonite here, but they have very long water channels that are internal to the structure. So they actually, when they break apart, they actually look more like fibers or needles. Now, the most common of these is called a pulgite, but things like oh gosh, what's it called? Asbestos is actually also in this group, where it has long fibrous needles here. Pulgite has a different aspect ratio, and it's not as cancer causing as it, but I believe that asbestos is in this clay group, which is the a pulgite group. All right, questions on types of clay. Now, these are all naturally occurring. They can be milled out of the ground, meaning that they are very commonly used nanomaterials because they're cheap. You don't have to make them. All you have to do is process them. And so we'll see those used extensively in our material. Now, note all of these materials here are going to be insulating, right? Electrically insulating. And all of them are going to have the same thermal conductivity as something like glass. Okay, because they're all aluminosilicates or silicates or something like that. So they tend to be used in making mechanical strengths, increases in tensile strength, and with the platiness of the Montmorillonite, barriers. But they're not used to create highly conductive materials. All right. All right, so now let's go off to the thing that we use for highly conductive, which is graphene and graphene oxides. So the idealized structure of graphene is a whole bunch of hexagonally arranged carbon atoms that are perfectly, aromatic all the way from end to end. Well, that's not really true. And in fact, perfectly perfect graphene is not soluble, it's not processable. So what we're looking for is graphene that has defects in it that makes it small enough to be dispersed in our system. And these are technically they have 2 dimensions, but they are a single layer in the nano phase because most of the structures are larger than 100 nanometers in size. But one of the more processable types is what we call graphene oxide. And graphene oxide just has enough defects that can hydrogen bond, like carboxylic acids or carbonyls right here, or carboxylic acids right here, or hydroxides that allow them to be processed and or dispersed in water or acid-based solutions. Okay, so a lot of people will process the graphene oxide and then reduce down or oxidize down off the groups and get closer to graphene after the fact. But most of the time, even though the perfect picture says it's this array, it's rarely ever that array. But the great thing is that there's enough pathways that these things are electrically conductive because of the pi conjugation, and thermally conductive because of the hybridization of the carbons makes them highly thermally conductive as well. So we can use both We can use these for both mechanical structuring, barrier structuring, and electrical conductivity. Okay. Questions on that? Yes.
So can we change their properties? Because, for example, I need to use the graphene or graphene oxide or graphite platelets for for building for preparation of concrete. But for preparation of concrete, don't need the thermal conductivity or that electrical conductivity. So can we prepare them that for certain properties only?
Well, no, because of the inherent nature of this, if you have any conjugation in your system, you're going to have electrical and thermal properties. Okay. For incorporation into concrete, you're going to want things that are going to bind to those other metals there, the calcium and the sodium and other metals there. So I would predict that if you see graphene used in concrete, you're going to see graphene oxide used in concrete because it's going to be more compatible with the ions you're using and the water-based processing you're using. Okay. Now, the more oxidized the graphene is, the less conductive it is, but also the less rigid it is, because it'll have more defects that won't hold it as rigid. So there'll be a balance there, but I imagine that graphene oxide is going to be more used in concrete because of its compatibility. Okay. Okay. Another thing that might be useful. Oh, yes, go ahead. Well,
I would ask you, are we going to conduct more detail about the dispersion techniques can be applied to these nanomaterials like graphene?
Yeah, we have a whole section on processing.
Okay, thank you.
I'm just introducing the materials now, and then I'm just telling you that we have to pay attention to which process we use. And then we have a whole thing on process, and then we have a whole thing on analysis. Okay. All right.
One quick question on your graph. I mean, on the image on the top right, what does the acronym BVMBSW and NS stand for?
Oh, those are types of voids. Big void, medium void, small void, and then this is a substitution, a non-carbon substitution.
Okay.
Sorry.
Thank you.
We'll talk a little more about that, but I just wanted to show you that it's rarely perfect. Usually there are some kinds of defects. And so, in fact, they have very fancy names for all the different edge types here. So, but yeah, big void, medium void, small void, and non-carbon substitution. So in this case, we have like a nitrogen or something.
So basically the defects only represented by the voids, or they can also be the impurities?
They can actually be added on purpose to enhance conductivity. They can be added to decrease conductivity. And they can be naturally occurring, or you can put them in there on purpose. Some people want perfectly imperfect and incorporate like 20% nitrogen, and that breaks down some of the electrical conductivity, but keeps the rigidity. So I'm not going to talk that much about that, but we will see papers where they look they want a certain level of imperfection to enhance their property. Okay. Okay, so the last of these one-dimensional items we want to talk about, these typically are synthetically made, and they're typically made through hydrothermal events where you take like zinc chloride and magnesium chloride, and then you heat it in basic water under high heat, and they form these layered oxides. And so we have the structure ends up being where we have one metal in the middle, right here in the middle, in the middle of the structure, and then a second one on the outside where it has hydroxides on all the surfaces. And then they're separated, the individual layers are separated by some counter ion and usually water. So imagine it's like a synthetic Montmorillonite that does not use silicon and aluminum. It uses all the other metals from the periodic table. And normally you want to mix the valences on this. You want to have a +2 or a +3 or something that'll kind of go together. So you can do aluminum, gallium, magnesium, etc. And so, but the Montmorillonites are naturally occurring aluminosilicates, aluminum and silicon only with very few other metals. Here, we're actually the predominant component is a number 2 valence or number 3 valence metal that's not aluminum or silicon. Okay, and so, and they have the advantages of that. Number one, you can make them specific sizes, and you can tune the conductivity. You can turn the thermal conductivity by incorporating different elements, but they tend to be non-thermally conductive and non-electrically conductive. Okay, questions on that? And these might actually incorporate very well into concrete because of their compatibility with water and the fact that they have a hydroxide surface. I'm not sure. We'll have to look for some papers on that. Okay, so now let's talk about 2 dimensions. We said in 2 dimensions, we're looking at maybe fibers or fiber-like materials. Okay, so the first thing we have to think of is that there's a difference between a nanotube, a nanofiber, and a full macroscopic carbon fiber. The first thing we want to look at here is nanotubes have a continuous graphite-like surface that goes around, but instead of being completely hexagonal, they have some 5-membered and some 6-membered rings alternating to the point where they can curve around to form that tube. And these have to have a continuous carbon scaffold all the way around to form the nanotube. Now, if you only have a single wall of this, we call that a single wall nanotube. Okay. If you can have multiple different little nanotubes, so a small nanotube, then a medium nanotube, and a bigger and bigger, we call that multi-walled nanotubes. Okay. Now, the difference in nanotubes and nanofibers is the nanofibers do not form that continuous wall around the entire outside. It is more of a cup shape. Sometimes they're bowl shaped. They're more defected and they're stacking on top of each other like pie clouds or by the impurities in those structures. They are not a single wall around, they're stacked together. And so they actually are not as strong as carbon nanotubes in the long axis, but can be stiffer because of that other interaction. Now, when we go to the macroscopic scale, we have carbon fibers, and carbon fibers are bundles of bundles of bundles of carbon that have been ordered, usually in a polymer and then pyrolyzed. But again, that XY dimension of that diameter is greater than 100 nanometers, and therefore that falls outside the scale of nanomaterial. And it's a filler that's used a lot to increase conductivity and rigidity, but it is not a nanomaterial. Okay. So the other things that fall into this are some natural clays like halloysite, which are fiber-like, nickel nanostrands, which increase the mechanical strength, but they also have a high electrical conductivity. And then there's some aluminum oxide nanofibers that halloysite is an aluminosilicate. This is aluminum oxide only, and that's a commercial material. And it again has low electrical conductivity, low thermal conductivity, but really increases the tensile strength, especially when the fibers are ordered. Okay, so if we look at, questions about any of this. All right, so if we look at the nanotubes and the nanofibers, again, they're different in the fact that our carbon nanotubes are almost always hexagonal, maybe a few 5-membered rings to give a rotation around here, and they can be single or multi-walled. They tend to be grown. I actually went to a manufacturing plant up in Ohio where they were growing it off little particles, some nickel particles in a fluidized bed, and they're growing out single wall nanoparticles from that. And so they can do it by a vapor phase process, growing off of a crystal catalyst. And that's actually how they make the multi-wall nanotubes too. They just use a different catalyst system. And these are great because you can keep growing them out to the length you want. You can have them good aspect ratios between the diameter and the length. You can control these. You can buy them in a bunch of different grades nowadays. Okay. Now, in concept, the nanotube is stronger than the nanofiber, because in the nanofiber, we have these stacks that are only held together with the pi cloud to pi cloud to pi cloud. But the way they're grown, they stack together very nicely, and they do have some rigidity, but they're not as rigid as the carbon nanotubes. And so what you'll end up seeing is, like here, your nanofibers will have a little more flexibility. They're not going to have as high a torsional strength because of the ability to slip along these planes. All right, questions on that? All right, so one of the natural ones is an aluminosilicate. It's instead of forming the flat sheets, because it has a defect system that makes one side smaller than the other, it actually rolls up into a spiral. Okay, so if we look at this right here, if we look at this structure here, we actually have a larger volume structure on one side than the other, and therefore it gives it a curve. Okay, so if you look at this, there's a water layer, the silicon and the hydroxide and aluminum layer is smaller in volume, and therefore it bends the system. Now, the great thing about halloysite is, number one, it's a naturally occurring material. It can be dug out of the ground. It has low electrical conductivity, low thermal conductivity, but it has a large aspect ratio, meaning that if they're ordered in the material, they're going to have a high effect on the mechanical strength of the material. But again, because they have this spherical, this rod-like nature, they're easier to disperse than the plate-like materials, okay? Because we only have to worry about trying to get one dimension included in the polymer, not two dimensions included in our polymer. All right, questions on the halloysite? Nope. Okay, so these are synthetic, and nickel nanostrands are used to make these things. You can make them out of gold, you can make them out of other things. They're also silver and silver nanorods. However, nickel is used more because of its oxidative stability. It's less costly than gold, and it actually has these interesting things where technically the fibers themselves are two-dimensional. They go off in one direction. However, because of the way they're incorporated, they're usually incorporated in a random distribution. So you end up with electrical conductivity through 3 dimensions, okay? And there's, of course, a little bit of oxide layer on the outside, but most of it is the metallic nickel, which does conduct electricity and heat. All right, and then, of course, there's the synthetic aluminum oxide nanofibers, the Nafion. It's made by a vapor phase process here. And when you pull these things off and distribute them, they end up being this material that you can disperse into polymer matrices. Again, low electrical conductivity, low thermal conductivity, but very high aspect ratio, very high effect on the mechanical properties. All right, questions on 2 dimensions? All right, that leads us to 3-dimensional things. So 3-dimensional things start with almost a molecular structure, okay? And they go up from there, and they can be amorphous or crystalline, like we talked about before, and they can be made by a wide variety of materials. The most common is going to be the oxides or hydroxides. And the reason for that is they're already in their oxidized form. They're not going to change properties turning into an oxide or hydroxide with exposure to air and water. So those are more common. Now, one of the few molecular structures that actually meets this goal is what we call POS, which is the sesquilial, anyway, it's this cage structure with silicon and oxygen. And then all these R groups can be all sorts of things. They can be these epoxies, they can be long chains, they can be acrylics, they can be styrene, they can be all sorts of stuff. But turns out that this structure here is just barely 1.2 nanometers tall. So it fits into our 3-dimensional structure. It's one of the few molecular structures that fits this, okay? Now, most of the time we're going to see clusters like this, clusters of the material, and they can be mono, they can be just the material like silica, which is SiO2, alumina, which is aluminum oxide, right there. titanium oxide, the hydroxide, which is also an oxide with a little bit of water in it. So they're in their oxidized form, so they stay how you made them. And they can be crystalline or non-crystalline. And the fact is, instead of being needle-like like the previous ones, they're going to be more spherical, or really they're going to be kind of faceted if they're small. Okay, now, if we grow just one thing by itself, it'll create these particles here. And then if you start growing one and then start growing something on the outside, you can actually get what we call core shells, where the core is going to be one thing, let's say a reactive metal, and then the outside is going to be a non-reactive oxide, so that you can get both the reactive metal protected by the non-reactive outside. So we can do a bunch of different things like that. And then so some other notables are this silicon carbide, okay? Silicon carbide is not very reactive, but it has a high thermal conductivity. So people will use that for a high thermal conductivity with low electrical conductivity. Nano silver is going to be a high electrical conductivity and thermal conductivity. And a lot of these other ones are going to be lower electrical conductivity or abrasion or ablation or something like that. Okay. Let's see. Also, yeah, nanodiamond also fits into this. Nanodiamond's a good one because it's got a three-dimensional structure, very high thermal conductivity, very low electrical conductivity. All right, questions? Okay, we're almost to the end. Oh gosh, running a little slow. All right, so I'm going to talk about the nanosilicon first. I'm sorry, nanosilica first. There's both. Nanosilicon is elemental silicon and is used one way. Silica is SiO2. Okay, so if we think about clusters of SiO2, if we just look at an SEM of them, these individual structures here, those are the crystallites of the silicon oxide. Okay, the silica are in those. And because of surface energy, they aggregate together. Okay, so we actually see these large macroscopic particles that sink out of solution. However, they're made up of these nanoparticles. And if we disperse them correctly, we can get these dispersed into our polymer system. So they naturally kind of aggregate together because of that surface area. However, if we modify that such by adding either like a surfactant or a carboxylic acid that'll disperse them, we can actually get very well dispersed nanosilicon particles. In fact, we can grow them not so randomly. We can actually grow them monodisperse now. And you can buy these as size standards that are monodisperse. They are plus or minus 1 nanometer out of 50 nanometers. So you can actually use them as your standards. They're common. They're dispersed in water with a little bit of surfactant. Okay. All right. I think I want to stop here because we're going to go to the nanometals next. Well, let me just introduce nanometals. Okay. Nano aluminum, nanosilicon, nano iron, any of the bare metals themselves can burn if they're on a small enough scale. So I will have a special topics lecture. It's probably going to be one lecture on nano explosives, nano pyrotechnics, and what explosives and pyrotechnics are. So the idea here is that you can take any metal, zirconium, you get it small enough, it'll burn. Uranium, you get it small enough, it'll burn. Iron, small enough, it'll burn. And so we can actually figure out the size particle required to make them burn and what you need to actually make them burn. Sometimes you incorporate an oxide with it, i.e. thermite. Copper oxide and aluminum equals an exchange reaction that'll burn. Copper oxide or aluminum oxide and iron will do an exchange and give you thermite. That would be nanothermite if you do that on a small scale. So look forward to that. And then we'll talk about the rest of these. Oh, that's the end. That's the last one I got anyway. All right, well, I'll add some more slides onto that and we'll talk about part 2 on next Tuesday. All right. Hey, just 1 minute to go. All right, perfect. All right, I'm going to go ahead and stop share and stop recording. And if you want to stop and ask questions,